The impetus for my research was the observation that University of Technology engineering students struggle to bridge the theory-practice divide, and that this is particularly evident in the design or project subjects, and even more acute when they are trainees in industry. I kept hearing industry partners talking about students not knowing the principles or not being hands-on. Now, the original contention in my research was that we do not fully understand the complexity of a problem-solving situation in the 21st century, particularly in the face of dynamic and evolving technologies, in relation to a relatively stable body of science-based knowledge. So I set out to look at how engineering practitioners apply different engineering disciplines in a real-world problem in different industrial contexts. So the aim was to understand what this disciplinary navigation looked like, so that we're able to look back at the curriculum and our teaching and shape it more appropriately for the 21st century. The research is theoretically located in the sociology of education and draws on the work of two key social realists, Basil Bernstein and Carl Mayton's legitimation code theory. I looked at the relationship between the different core disciplines underpinning multidisciplinary engineering, their different knowledge structures or organizing principles, the fact that on their own, which we tend to teach in silos, these disciplines require different ways of thinking. And I wanted to understand what it meant when these different disciplines come together in a problem-solving moment. The engineering region at the heart of my research is mechatronics engineering, which is the computer control of electromechanical systems, the kind of engineering you find in manufacturing. Now, its core disciplines are physics, mathematics, and logic. I've arranged the key elements of a mechatronics curriculum as a Venn diagram to demonstrate the disciplinary spread. Now, in Bernsteinian terms, here on the right we have the traditional physics-based engineering regions, mechanical and electrical. These are regions underpinned by physics, what Bernstein terms a hierarchical knowledge structure. We have specific concepts strongly sequenced that absorb lower concepts. Ohm's law is an example, or force. Now, in the center, and applying across the spectrum, is mathematics, which is a strong horizontal knowledge structure. This simply means that there are different mathematical languages which you could apply to the same phenomenon. Each language has strongly recognizable concepts or rules that are not necessarily applicable to a different mathematical language. Now, the upper left are regions that are underpinned by logic, the disciplinary basis of programming and control systems. Now, this is a weak horizontal knowledge structure. Weak meaning that there are choices that are context dependent, like languages themselves or social science. In other words, the phenomenon itself does not dictate the knowledge form in the way that motion is governed by Newton's laws or voltage is governed by Ohm's law. These kinds of knowledge are weak in that they borrow concepts and rules across families of the same type. They're constantly changing. Things become redundant. Now, each of these structural knowledge types requires an entirely different way of thinking, of learning even. They represent a different kind of code, and we tend to teach them in silos in their specific subject streams. But the question is, how do engineering practitioners work with such very different forms of knowledge at the same time? The analytical tool used to look at the problem-solving moment comes from one of the legitimation code theory dimensions, specialization, specifically the concept of epistemic relations. This is about the what and the how of knowledge. Now, the vertical axis is about the phenomenon in question, how strongly it is bounded by recognizable and legitimate principles. The horizontal axis is about ways of approaching the phenomenon. The stronger the rules, the stronger the so-called discursive relations. Now, the epistemic plane gives us 4 codes, 4 ways of thinking. The top right is purist, recognized principles and associated procedures, precisely like Ohm's law. Doesn't matter what language you speak or where you live, the principle of the relationship between current, voltage, and resistance is consensually accepted. The bottom right is recognized methodologies. Doesn't matter what the phenomenon is. This is like following a formula, the structure of an experiment, applying lean manufacturing rules, mathematics, or economics. The top left quadrant is called situational insight. There are many possibilities for addressing the same strongly bounded phenomenon. Choosing a new cell phone, for example. What I want to do is fixed, but how I do it is variable. I have a range of choices to choose from. The lower left quadrant is where there isn't a strongly bounded phenomenon or any fixed ways to do things. This could either be because now we're not focused on knowledge, but on knowers where different or other things count, or because there is no legitimate or recognizable practice. There isn't a strongly bounded phenomenon that all understand or adhere to, or recognizable procedures through which we can approach something. Now, each of the previous knowledge structures we looked at, and each of these insights represent a kind of code, a way of thinking, and each code or insight is significantly different. How did I use this in my research? Now, very briefly, I had 50 volunteers working as mechatronics technicians or technologists in 3 different types of automation environments. They completed a questionnaire describing their context, the most recent problem faced, and a technical description of how they solved a problem. I then selected 18 of 27 responses and conducted a second phase, a reenactment interview. This meant they took me through the actual problem with the real artifacts involved in that problem, which I video recorded. Now, the third phase involved getting their supervisors and my industry experts to verify my analysis. Now, I used the epistemic plane to map their approach to and analysis of the problem and the subsequent synthesis of a solution. In other words, I try to surface the disciplinary basis of their problem-solving process. Now, here we have a range of maps that demonstrate some of the problem-solving processes undertaken by different participants. Now, one key finding was that the scale of the environment dictated a preferred insight, a way of thinking. The larger the company, the more doctrinal the insight. In other words, practitioners tended to start here and be governed by the procedures in that context. A second key finding was that the more holistic problem solvers in the different environments displayed an anomalous high achievement in both mathematics and the logic-based subjects. Now, this is not common in this particular qualification. A third finding was that each of the different environmental types revealed a different problem-solving process pattern. In all cases, there was a multi-layered cause-effect relationship between the disciplines in the actual problem structure in relation to a particular problem solver in his or her problem-solving environment. Now, what emerges from the research is that successful problem solvers recognize the different disciplines and aspects of the problem, and use explicit code shifting techniques. They engage in practices in all four quadrants, and they shift consciously between them. Now, the technical language they use changes depending on the context, whether it's for a report or verbal update to their managers or a discussion between colleagues on a production line, for example. These successful problem solvers appear to take a macro view, taking into account the people, the situation, the principles and procedures of each aspect of the problem. This means that for every problem-solving situation, there are too many contextual variables for us to prepare our students. I do suggest in the research that we need to enable two things in our teaching. The recognition that the differences between disciplines are essential. They mean different ways of thinking, and by extension, different ways of teaching and learning. Secondly, we need to enable a more conceptual grasp of the reality and principles of different practice contexts. We cannot hope to mimic or simulate all the possibilities that our students will encounter.